Welcome to today's webinar, Create with Intel an IoT Gateway and Establish a Data Pipeline to AWS IoT. Our presenter today is Martin Kronberg. Martin is a technical evangelist for Intel's Developer Relations Division. He is responsible for running workshops, creating content, and supporting the developer community in the Internet of Things environment. He is skilled in developing applications that interface hardware with cloud analytics across a wide range of topics, including computer vision, robotics, and language processing. Today with us, we also have Nicole O'Malley, AWS Product Marketing Manager, Tara Walker, AWS Technical Evangelist, and Olawale Oladahin, Solutions Architect for AWS IoT. They are our webinar moderators who will be engaging with you and answering your questions throughout the presentation. Martin, welcome. The floor is now yours.
Hi, thank you for that great introduction. My name is Martin Kronberg, and I will be talking about building out an IoT framework with Intel and AWS. Before I dive into the specifics of this project in particular, I kind of want to discuss Intel IoT architecture at a bit of a higher level. So, if you start looking at IoT, it kind of starts with endpoints. Things like sensors and actuators, types of devices that gather data and interface with the environment in some way. A simple example could be a thermometer to read temperature, and then a relay to turn on HVAC system. On the other side of that IoT architecture is cloud analytics. And this is where a lot of the really interesting things happen in terms of big data processing, machine learning, natural language processing. Then all of a sudden that thermostat can do more than just tell you the temperature right now. It can begin to tell you the temperature in the future using predictive analytics, for instance. Now, between the things and the cloud, there's going to be a gateway and there's going to be a data center. A data center is the realm of Xeon Phis and other high-end Intel processors on which a lot of the cloud analytics run. But what I want to talk about today more is that gateway, or specifically Intel gateways. So the things need a way to communicate to the data center. And there's going to be a few issues that need to be overcome to make that happen. First of all, many endpoints do not have a way to connect to the internet themselves. They have a serial connection, maybe a USB or a Modbus, some kind of short-range radio like Zigbee, Z-Wave, Bluetooth. And the gateway can act like a data collection hub by collecting data from all the sensors and then establishing a secure connection up to the cloud. Having a central data collection point also allows for a few things to happen. First of all, even if each one of your sensors could send data individually, you really don't want to have multiple connections up to the cloud. This is going to make your system inefficient and insecure. If you have a lot of connection points, it's going to essentially make your IoT system have a larger surface area for any sort of vulnerability attacks. So if you can gather all that data into the gateway, you can do any kind of pre-processing on it that you need, you can secure it, and you can connect to the cloud through that gateway. Now, today I want to talk about specifically the NUC Gateway. So the NUC is a so-called next unit of computing, which was a term coined by Intel. And it refers to a series of small, customizable PCs, which come in a wide range of specifications. And the specifications range from lightweight prototype devices, which I will be using for this demo in particular, all the way up to a more rugged industrial grade type device, which has a more powerful processor and a larger range of connection protocols supported. So what are the benefits of using a NUC gateway for your IoT project? Well, one of the things is scalability. So you can adjust just the right amount of compute power for your project in particular. And you can find a balance between power requirements, heat, the cost of your deployment, and balance that out and basically find just the right amount of power across the same architecture. So, for instance, if your project all of a sudden grows in scale, you can scale up from an Atom up to an i7 while maintaining all of your same code. You won't have to rewrite it for a different architecture. Intel's IoT ecosystem also is powered by open source technology across the board. So what this means is that it has a much higher level of interoperability than if we were using, let's say, closed source systems. And by using open source technology, that means you can use exactly what you want from our ecosystem. We have, for instance, MRAW. I'll talk about that a little bit more detail, but it is a open sourced interface library that Intel has been actively developing for years. And you can take what you need from the APIs, you can take what you need from those libraries, and if you don't want to use the whole thing, you can just use what you want. Also, there's no licensing to deal with. And all of our gateways run on Linux systems. This project in particular runs Ubuntu 16 server. It uses the MRAW open source libraries for all the sensors, and all of the code for everything is up on GitHub. So it makes it really easy for a developer to access all of that technology. So I mentioned MRAW, and MRAW is a series of interface libraries that can basically interface to basically just access the pins, turn on and off digital pins, take analog readings. And all of that is built into the MRAW libraries, which also control all of these other low-level protocols. Now, on top of MRAW is something called UPM, which is the Useful Packages and Modules library. Now, this is where a lot of the strength of the system comes from, because these libraries support hundreds of different sensors. And it goes from basic prototyping sensors all the way up to more advanced, hardened industrial grade sensors across a huge number of protocols. So, you have your Modbus and CAN bus support, as well as just simple analog voltage inputs, which basically means that as your project grows from a prototype to a production, you can use the same code and just switch out which sensors you're using. It makes production really simple. Another thing that is really powerful about Intel's IoT ecosystem is the open standards in IoT. So Intel is part of two consortiums that I want to talk about briefly. One being the Open Connectivity Foundation, which is a group of about 300 members, including Intel, Microsoft, Qualcomm, Samsung, among others. It focuses on creating standards in connectivity and certifications for IoT devices. Out of this foundation has come IoTivity, which is an open source project hosted on the Linux project, which focuses on connectivity between various devices and using various protocols such as Bluetooth, Zigbee, Z-Wave. And basically the idea is to create a standardized system to connect and certify your IoT devices. Intel's always been pretty big on creating standards like USB. And so we're definitely taking the steps to kind of ensure that you'll be able to connect all your devices to all of the hardware, to all of the services that you need. And along with that, there's also the Industrial Internet Consortium that was founded in 2014 by AT&T, Cisco, GE, IBM, and Intel. Right now it has about 250 members, and it's less of a consortium focusing on standards and connectivity and more of a consortium that just focuses on building out an ecosystem for the industrial internet. And essentially just making sure that all the big hardware and software companies can play nice with each other and really allow developers to utilize all of that technology. And like this webinar and webinars like it is kind of of a testament to that attitude, where we have Intel hardware interfacing with Amazon's cloud, and we're all working directly with the production teams and the marketing teams and everything else to make sure that it all works together as best as we can. And one final thing that I want to touch on is the idea of a path to product. So, I deal mostly with building out prototypes and teaching developers how to build prototypes. And this project in particular that I'll be talking about is also a prototype. But then the question is, once you have that prototype, what's the next steps? And Intel has a lot of developer-focused resources that outline how to move from that prototype towards a real product. We have, an entire article is devoted to showing the developer how we created a number of product demos, using industrial-grade gateways and industrial-grade sensors. And these products include many different verticals. So we have retail demos, we have smart home demos, transportation demos. And as you go through this so-called path to product, a lot of the strengths that I talked about kind of really come into their own. Because you can use all of these open source samples. You can borrow from them, you can use them in its entirety. You can scale your product up or down. So if you start with a Atom-based prototyping board, and you realize that you need more power for, you're running some kind of local computer vision application, you need to scale up to an i5 or i7. And once again, you can do that, no problem. And so if you're interested in learning more about this sort of process, there's a lot of information up on software.intel.com/IoT. Okay, so specifically of what we're looking at today. It's going to be a project that creates a framework that outlines how to basically take sensors, connect it up to an Intel gateway, and then send data up to AWS IoT and have AWS Lambda run a very simple rules engine on the data. So essentially just monitor that data for some kind of fluctuations, or if a data reading is out of some sort of nominal reading. So just to be fully transparent, what's running in Lambda for this particular project isn't anything that you couldn't do locally as well. But I felt that to keep it as simple as possible in order to establish that framework. But you could use this framework for any number of much more advanced or cloud analytics applications. For instance, if you wanted to leverage AWS's recognition, visual processing, for instance, like that's not something that you could really do at the edge, but you could use this same framework to pipe your images up to any number of services. So. And you can kind of see the overview of protocols as well. So we're going to be using MRAW and the Fermata protocol to connect between the Intel NUC and an Arduino 101. And if you're not familiar, an Arduino 101 is essentially a Intel Curie SoC or system on chip, which is mounted on an Arduino Uno form factor. And we'll be using that particular device as a sensor hub to connect a couple of Grove sensors. Grove sensors are prototype sensors which have like really simple plug-and-play sockets on them that provide power, ground, and 2 signal pins without having to breadboard anything. So it makes it really simple to kind of plug everything that you need and then go from there. In order to communicate to AWS IoT and between AWS IoT and Lambda, we will be using MQTT, which is the Machine Query Telemetry Transport protocol. I believe that's what the acronym is. And this is a fairly standard, I mean, almost the standard IoT communication protocol at this point, which basically just is a pub-sub type of system where you have a broker that accepts subscriptions, and then you will basically publish data to a topic and then read data from a topic. And we will see more on that when we get to it. Okay, so first thing up is setting up the sensors. Like I said, pretty straightforward. You can see that I took an Arduino 101 board. I plugged it all the sensors that I needed in this case, a light sensor, a couple LEDs, and an LCD screen. So I will be using the light sensor to read the light in the room. And if it goes above a certain threshold, our rules engine will basically send an alert down to the LCD, which will say, like, danger, it's too bright. I'll leave it up to you and your imagination about what kind of things that can be used for, but, you know, monitoring some sort of environmental variable and basically having an alert is something that is pretty common in industrial applications. And now I would like to go through and basically show you the process of all of the coding that I did in order to get this project to actually work. So if you'll give me one moment. Okay. Okay, so first things first, you know, you need to have an AWS IoT account and sign into the console. The console is going to be where you access all of the Amazon services, so AWS IoT, Lambda, etc. And the first thing that we want to do is create a thing in the AWS IoT registry. I already have a couple made, but you know, we'll make a new one just to see how that goes. Give your thing some kind of name. I'm gonna keep it simple. Just call it, you know, Gateway. And once you create that thing, it will give you all kinds of ARNs and API endpoints, as well as show you the different topics for the shadow. So the shadow state is something that I'm not talking about in this particular project, but it is essentially a set of specific MQTT topics that handle the state of the machine. And that could be a topic for another webinar. But and in order to connect the gateway up to that registered thing, we're going to be using a Linux OS and a Node.js runtime environment. We're going to download the connection package, and at this point, AWS will generate all of the certificates that you need to connect, because in order to connect up to AWS IoT over this MQTT protocol, you need to have a series of certificates in order to be able to publish and subscribe to any topic. So this is a way of ensuring that only certified devices are able to access your data in the cloud. Once you download the connection package, it will actually really helpfully give you the next steps to do. So basically, you need to push that connection package onto your device, run the setup script, and then see if it's all working. Now, in order to push that connection package onto the gateway, you can use any kind of FTP or SCP protocol. I like to use FileZilla. It's real simple. It has a nice little file browser. So I put in the IP address of my NUC, my username, my password, port 22. Connect up, and then I am able to push over my code. So, I mean, really, I'm just running a headless Linux server here. No, nothing too crazy. Excuse me. Once I have everything on there, I will open up a terminal, and I will SSH onto my board. Once again, IP and password. You can see what's there. There's a package. I will unzip it and make it an executable. So chmod plus x. This is once again like another security thing. So you can't just run any script without specifically saying that it's a executable script. You run it, and what the script is going to do is a couple things, actually. So first of all, it scans your local environment to see if you have the AWS IoT SDK installed. And this is a series of Node.js, specifically because we're using a Node.js runtime, Node.js modules to connect up to AWS services. If you don't have it, it will pull it off of NPM, I believe, and install all of those modules. It also has the certificates built into that zip file. So then once it installs the SDK, it runs a sample pub sub application using those certificates. And so then you're right away able to see back at the last screen of the connection wizard that you are getting signals from your device. And in here, it's just a simple integer counter, 1, 2, 3, 4. You can also test the connection the other way by sending a message to the device. And then you will see that if everything is working, you will see that message appear in the terminal. So here we can see that the basic connections are working, our certificates are working. Okay, great. So now let's write a specific piece of code to interface the gateway to AWS IoT. So I started with the example that they have in terms of the AWS IoT device API calls, and integrated in some code from MRA and UPM. And so at the top is basically I am requiring MRA, I'm setting up a platform using Fermata, and I'm pulling in a couple of sensor libraries. If you're curious about, how do I know what kind of code to use? Like I said, so all of this stuff is up on GitHub. So in a moment, I will go to that GitHub, and you can kind of see a pretty simple way of finding all the API calls. Any minute now. Okay, so here is the UPM GitHub. If you go to examples, you can select your library, you can select your language of choice. As you can see, we support C++, C, Java, JavaScript, as well as Python. And it's, you have basically a list of all of the sensors. I searched for an LCD sensor. I have the code here, and basically I can pull out the API calls that I would need in order to get that Grove LCD sensor to work on my board. Pretty straightforward. So require the library, create a new LCD, and then you can start doing things like set color right, set cursor. The next thing is setting up the AWS IoT environment. So I'm using AWS IoT Device SDK, as well as the certificates, so the private key, the certificate, the root CA, and I am also using the host name. And the host name is what you would get from the AWS IoT service once you create your thing. It's basically just an endpoint. And I believe if I didn't show that here, it's pretty straightforward once you create the thing. I created a simple function to read the light value and then publish that light value to a topic. So this topic is, like I mentioned earlier, is an MQTT topic. There is an MQTT broker that runs on AWS, and I am using my AWS things Webinar Gateway, which is the name of my thing, /sensors, which is where I'm sending all my sensor data. And I am sending it as a JSON object, so I can parse it out easier. And this will be sent out once every 1,000 milliseconds or once a second. Likewise, I'm also subscribing to a slightly different topic called Webinar Gateway /input. Now, this is going to be the input from the Lambda rules engine. And the final piece is basically specifying what happens on different cases. So when that device gets a message, so on message, it will display that message in the terminal and then also pass the message on to the LCD screen. So there's no local logic here at all. It's really just taking the message straight from Lambda and putting it up on the LCD screen using that display.write API that I mentioned earlier. We have a couple other functions on connect, close, reconnect, offline error. Basically just, hey, console log, something happened other than what we thought. Once again, going back to FileZilla, we will put our webinar code over onto the gateway. And then, before we run it, we're going to go and set up the Lambda code. Now, so if you're not familiar, AWS Lambda is a way to run code in a virtual runtime environment without having to provision an entire EC2 server. It basically just gives you just enough server space to run your code, and you can do that in a number of different runtime environments. And it's essentially going to be the mirror to the local gateway code. We're going to start with a blank function, and the first thing we do is set up a trigger. So basically meaning, when does this function get triggered? In our case, we want to use AWS IoT and create a custom rule. Rules are based around using an SQL statement. So I'm going to give it a name, I'm going to give it a short description, and then I'm going to say when to trigger this Lambda function based off of those MQTT topics, once again. So I'm going to select all messages from my topic of sensors, so that using the first part, well, I guess I could have just copied it from the code, but so the AWS things gateway, and then instead of using shadow update, it will be just /sensors. And actually, at this point, I've realized that I'm using two different things throughout. So in case you guys are very very observant, so the /things/gateway and /webinar gateway, that was just my mistake. I should only be using one thing. I think I was working on two different things in parallel and got a little bit confused. But anyway, so I'm basically saying that this Lambda function will be triggered when any message comes to that sensor's topic. Turn on the trigger, and here I can write Lambda code. So give the function some name, give it a description, choose the runtime. In this case, just use Node.js 6.10. And then we'll be able to edit your code in line. Now, so right now, as far as I understand, Lambda only has the AWS IoT SDK as a default module. If you want to add any other modules, you need to download them locally and then zip it up along with your code, and then put that onto Lambda. So that way you can bring in additional modules. At least that's the way that I've done it. I don't know if there's a better way or not. So for the code, we will copy and paste some code in there. And basically we're using a similar method to connecting to AWS IoT as we did to the gateway, where we specify an endpoint. And we don't, as a note, you don't have to worry about certificates in Lambda, because we're going to be using an internal certification system, which I will show you in a little bit. But in terms of the Lambda code, what was I going to talk about? So you have the endpoint, which is where Lambda is going to be connecting to. It specifies the region. I have a state update variable, which basically means that this is what is going to be sending back to the gateway. You set up a, right, okay, sorry. So this is where the RESTful API endpoint comes from. And that's the same one that I mentioned in the gateway code. So you set up an exports handler function, which basically deals with what happens when the Lambda function gets called. I pull out the light value based off of the event.state.reported.light value. So that was that JSON that I sent up to AWS IoT earlier. You can use whatever structure you feel like is most convenient for you, but I'm borrowing from the shadow SD or the device shadow structure. Basically set up a really simple engine. If the light value is above 10 lux, you say it's too bright. If it's below 10, you say it's nominal. If it's exactly 10, I don't know. Hopefully it never gets to exactly 10. With the actually sending of the data back down to AWS IoT, we just create a parameter that has the topic that we'll publish to, so the webinar gateway / input, the payload, which is going to be that state update as a JSON, and then we'll use the IoT data.publish to actually send that data up to AWS IoT. Now, in order to actually allow Lambda to communicate to AWS IoT, we have to set up some permissions. And we're going to do that by creating a role from a template. There are many different policy templates that you can start with. I just use a simple microservices permissions. It's kind of just a general one. But we're going to have to go in and add a few extra elements in order to get everything to work properly. So in order to do that, we will go to the IAM Service Manager through your console and pull up that policy. I'm sorry, pull up that role. And in that role, we can attach specific policies. So we have a couple policies there that came with that microservice template. We need to also add a AWS IoT full access. So basically read-write permissions to the AWS IoT topics, as well as I want to add a policy for CloudWatch. Now, CloudWatch is a monitoring system for Lambda, which will basically let you, and if you add this CloudWatch full access, you can basically write to the logs and read from the logs. And this is a really good way of troubleshooting anything that goes wrong with your function. And I will also briefly show how to use that. So with these policies in place, we're good to go with our connection. And the code is ready to test. So a good way of testing the code is you can give it a specific message, which it assumed came through that SQL statement. In this case, I'll be sending it a JSON of the form that I'm sending from the gateway, so state reported light value. And in this case, I'm going to use 20, so this should be too bright. Click Save and Test. And then down at the bottom, you will see the log output. And you see what the event that it got, the topic that it wrote to, as well as saying, danger, it's too bright. Okay, great. So that works. Now, if we want to see more in-depth logs, we'll go to that CloudWatch here. And basically here you have all the logs from all of your functions. And you can break, it's by the time, you can kind of expand them, see what's going on. I find I use this a lot to debug things because I feel like sometimes the log output from the Lambda isn't explicit enough. It'll just kind of say, hey, I errored out. And in order to find out why it errored out, you have to go to CloudWatch and say like, oh, I'm not using the right API call or something. Another way to sort of test this is in AWS IoT, there is a MQTT client service. And that's, if you go to AWS IoT, on the bottom left is a test. You basically subscribe to a couple of topics. In this case, I'm going to subscribe to the input and the sensors topics. And to the sensors, I'm going to send that reported light value. And I should see that the Lambda function sent back a LCD state to the input topic. And also I should see that if I put 5, it should say nominal. If I put 20, it should say too bright. So, okay, great. So everything's working. And now I can go back to my gateway where I have the gateway code. And I will run my code here, just using Node. Node and then webinar code.js. Launches, starts reading in values. It will then tell me when it's connected to the AWS IoT service here. And now we should see two-way communication where we have light coming in, or sorry, we have a sensor value coming in, and then an LCD state coming out. And as a final piece, we can kind of see what this looks like in the real world. And I took a short video of the light sensor and the readings from the LCD. So it'll be going between nominal and too bright, depending on if it's getting a threshold amount of light or not. So yeah, and that is the demo. And I guess at this point we can open it up to questions. That is all that I had to talk about.